In this third video, I'm gonna jump ahead a little bit and I'm gonna derive the Navier-Stokes equations themselves. Now we're interested in prototypical equations. We'll find, however, that the second and the third prototypical equation are simplifications of the Navier-Stokes equations. Yeah, so in order to derive those, I'll need to derive the Navier-Stokes equations first. Now the procedure is going to be very much the same as the one we just did on the advection diffusion equations. We're going to create a control volume, we're going to specify certain balance laws, we're going to have to balance some internal time derivative of a volumetric quantity and balance that whatever flows in via the surface. Next step is going to be a divergence theorem. Now, this is not a class on fluid mechanics, so I will not go into too much depth and detail. I highly encourage you to look the details up yourself. Nevertheless, clearly, if we spend a semester working with these equations, then it's important that we have an idea of what they mean and where they come from. And that's why I have chosen for deriving these. So the Navier-Stokes equations, what they really are, is a set of equations, one that stands for the mass conservation of the system, and then a combination of equations that are about the momentum conservation of a fluid. Yeah, so these are mass conservation and momentum conservation of a fluid. So conservation is a balance law. We can write a control volume, or we can draw our control volume. And I'll do one for the mass and one for the momentum. Then we have a certain flow running through this control volume. So our material is passing through our reference frame. Try and draw the same, roughly the same lines, left and right. So on the left, I'm going to derive the equations for mass conservation, on the right, the ones for momentum conservation. So what's the total mass in a system like this? Well, it's going to be the integral of the density over our control volume. What's the total momentum inside of our control volume? Well, that's going to be the integral of rho times the velocity over that volume. So our balance laws are now simply going to be time derivatives of these quantities balanced out by whatever flows in or out in terms of these quantities across the surface of our control volume. So we have a time derivative, d dt, of the integral of our density. And a time derivative is going to be equal to whatever flows through the boundary. Well, that's just purely the advective part, right? That's the same thing as what we discussed in the advection diffusion equations. And that ended up being negative integral across the boundary of u times the density dotted with normal. So how do we do that for our total momentum? Okay, well, let's start simply with the time derivative of the amount of momentum inside of our control volume. That is going to be equal to, well, we actually also have a source term. So let me start with that one just to have that one out of the way. That's going to be equal to the the external forces acting on the material inside of our volume. We have F times the omega. So that's the volumetric term. Now the rest are going to be boundary terms. So in part, we're also going to have this advection of momentum. So we have our momentum expression, which is rho times u. So no, sorry. First we have our advective field, u, and then we have rho times u, or u times rho. That has to be dotted with the normal, right? So this is our advection of our momentum equation. Now, in order for this to work out in terms of index notation, we have to end up with a vector valued expression, right? Because this is vector valued, this is vector valued, so this has to be vector valued. So we're going to have to dot something with n to produce a vector. So that's going to be a tensor, meaning that this is going to be a tensor product between u and u. ds, and we have a negative sign, right? Just like we had before. Now the second contribution to the change in momentum inside of our control volume is going to look a bit more like this force term. It's actually going to be the tractions around the surface. So we're going to have another boundary term of the traction across the surface. The traction is going to be equal to the stress tensor dotted with the normal vector. So we actually get this term here. Okay, so now we have relatively equivalent equations on the left and the right hand side. How do we proceed next? Well, we're going to do exactly the same thing as what we did for the advection diffusion equations. We're going to replace our surface integrals by volume integrals by making use of the divergence theorem. Additionally, I'm going to move the ddt inside of the integral. And I would end up with the statement that the integral of our volume of the time derivative of the density is going to be equal to minus, and now we simply replace, this is a vector valued function that was dotted with n, and that would end up being a volume integral of the divergence of that quantity. Now I can do the same thing on the right hand side. So I'm starting every time with the left hand side because that is the seemingly easy version, but really I'm just repeating the same set of steps. And so I'll do the same things here. And then I have integral of my control volume of dt of rho u. It's going to be equal to, I'll first do the divergence theorem on these volume integrals. So that gives me minus u tensor product u times rho. I think it's slightly nicer to write this the other way around. So I have minus rho times u tensor product u. Ah, now I'm going a little too fast, sorry. So we have the divergence of that, of course. I also have the divergence of my stress. And I still have my source term. Now we can also see that all terms inside the integrals are still vectors. On the left we have rho times u, that's a vector. On the right we have the divergence of a second order tensor, well that's a vector. And we have here a vector, and again we have the divergence of a second order tensor, also gives me a vector. Now the next trick that we used for the advection diffusion equation was to say that this domain is actually arbitrary. And that's how we are left with a partial differential equation. Because we're going to say that this then has to hold pointwise, giving me that the time derivative of our density is going to be equal to and opposite the divergence of u times the density. And here I'm going to have that the time derivative of my pointwise momentum is going to be equal to the divergence. And this is actually a term that we typically already move to the left hand side, so I'll do that right now. So that gives me a plus here. It's going to be equal to the divergence of the stress plus the force. And these are already the Navier-Stokes equation in a slightly more general sense. Now the thing that we're still missing though is a constitutive relation for sigma. And a constitutive relation that we typically use for most fluids that we're interested in, water and air, is that of Newtonian flow. So we're going to assume a constitutive law of Newtonian flow, or Newtonian fluid. And a Newtonian fluid is what it's saying is that, well, in our discussion on the relevant physics and the constitutive laws of the relevant physics, was that we should not relate our stress to a strain, but rather to a strain rate. And if we're thinking about the material behavior, then we have this slipping behavior of the different atoms. And it will be exactly the slipping behavior that induces a shear stress. And the shear stress is just going to be proportional to, again, the gradient of our velocity. That's the strain rate. So what Newtonian flow really means is that the shear is going to be proportional to partial ux, but then in partial y. Right? So I'm interested in the time or the derivative of this difference of the flow in x direction, but the difference in the y direction. Yeah? So the partial ux over partial y. So what kind of constitutive relations does that then give for sigma? Well, I get that sigma is going to be equal to a pressure which means that the rest has to be deviatoric. And then we have gradient of u plus gradient of u transpose minus 2/3 mu times the divergence of u. So this is a deviatoric part. Right now we're calling mu the viscosity. And this relates to precisely this proportionality. Yeah, so the Newtonian flow only has a relation between the shear and the velocity, and not to any kind of bulk behavior. The bulk behavior is then still set in the pressure. So that's actually going to be one of our state variables. Now that's the first assumption that we'll have to make, assumption if you will, a closing relationship. So the second assumption that we could make to simplify Navier-Stokes equations is precisely again the one of incompressible flow, so incompressibility. So what does incompressibility mean? Well, in the talk about advection diffusion equations, we saw that if a divergence of a vector field is zero, then it's about an incompressible vector field. So where does that actually come from? Well, incompressibility means that the density doesn't change per time. So we have the time derivative of the density at any point is going to be equal to zero. So if we then look at the left side here, then we find that ddt of rho is equal to 0, which means that minus the divergence of u times rho is going to be 0. Or maybe I should say, I'll say this slightly differently. Incompressibility means that rho is constant, which means that the time derivative of rho is equal to 0. And it also doesn't have any spatial derivatives. So that means that the left-hand side here is 0, and the divergence of u times rho has to be 0. So we get minus the divergence of u rho is equal to 0. Since rho is constant, we can pull that out, and we simply get that the divergence of u is equal to 0. And that's why that's a relation that relates, that defines or corresponds to incompressibility. Now, this is actually also something that shows up in our constitutive law. Right, so for incompressible flow, we can also drop this term of our equation. And then actually this simplifying the constitutive law becomes times the symmetric gradient of u. Yeah, so this is also a way of probably twice the symmetric gradient. Yeah. Let me see, am I actually using that in my notes? Doesn't look like. It doesn't matter. Okay. So that's the simplifying constitutive law for a Newtonian flow. Now, if we substitute this into our momentum balance equations, and we make use of this incompressibility constraint or incompressibility condition in the left sets of equations, then our new Navier-Stokes equations are going to be dt of u plus the divergence of rho u Okay, so I'm already dividing by rho on both sides. So then this guy drops out. I feel like I'm doing something wrong here. So there's two ways of writing these equations. I'll jump straight to the result. I probably should not have written this. This is probably confusing. Let me rewrite this. So that's simply gradient of u plus transposition. There we go. So then I have here the divergence of plus F divided by rho. So this is what we typically call, we typically write this as the pressure. So most of the time if you find the Navier-Stokes equations written in this way, then they would simply replace P over rho by a new effective pressure, in the same way as they would typically replace this simply by F. And this guy now becomes mu, and this is the kinematic viscosity. Okay, so I did some shuffling around here on the left-hand side, which I was a little bit uncertain about how I want to motivate that. I don't think I want to go into the details here. The point is, or the issue is, that we have here a time derivative of rho and a divergence of this second order tensor. Now, if rho is constant in space and time, then we can simply factor out this rho and then we're fine. Yeah, and that's how this rho ends up on the right-hand side here. We can actually also get rid of rho in many of these terms by actually making use of this relation. And I wasn't sure if I want to do that. I don't think I want to do this. And so I would encourage you to have a look at this yourself. So what you can actually do is by writing out all these different differentials, then you can factor out exactly this term. And you would get a result that looks like d dt of rho times u plus rho. So you would get two terms here. If my memory serves me right, you would also get a term here that looks like the divergence of rho u times u, and then you would get d dt of u times rho plus, yeah, okay, plus this term plus rho times u dot gradient of u. Okay, and that's going to be equal to what we have on the right hand side here. And this is already actually cancelled by our mass balance, right? So we have ddt of rho is equal to minus divergence of this guy. So that is what we have here. So this term cancels whether it's incompressible or not, and we would end up with this term, again, whether or not this is incompressible, and then we can divide by rho. Again, also whether or not we assume incompressibility. So I do actually encourage you to look into this because it's quite interesting. So the point, I guess, that I'm trying to make here is that there's multiple ways of writing these equations. Unless you do it yourself, it is slightly confusing at which point the assumption of incompressibility is assumed. If you assume it right from the beginning, then you can cross out rho almost everywhere, and then things simplified quite quickly. But you can also leave that assumption all the way to the end, which I suppose is a little cleaner. Irrespective of how you would do this, if you have an incompressible flow, then this is going to be one way of writing the Navier-Stokes equations. Let me get rid of my short notes here. Yeah, so I encourage you to look into how that derivation works. But as I mentioned in the beginning of this lecture, the point here is not to give you a full overview of what the Navier-Stokes equations are about. So this was the momentum equation, and the second set of equations, the mass balance equations, they also simplify into simply the divergence of u is going to be equal to 0. And then this is going to be the Navier-Stokes equations in the way that I'll make use of them most of the time. Okay, so if you're interested in any more of the details, then I think there's ample material to find with just a few keywords in Google. I would encourage you to try to write this out yourself. I think it's a good learning process to find out where certain assumptions come in, the difference between kinematic viscosity and the typical viscosity here. Then if you move back in time a little bit, and you also notice that at some point I was writing this as twice mu times the symmetric gradient. That's another way of writing this. And I think it's definitely worthwhile to have a look at these different notations and understand that they're all saying the same thing, because else you might get confused if you're not sufficiently familiar with that. And you start reading into this and you get confused about why they would write, or why they can write these equations in multiple different ways. Okay, other than that, I hope this was a good introduction to these equations. After this, I'll actually use these equations. I'm going to simplify them, and then we obtain our last two prototypical equations. Thank you.